This video we're going to take a look at atoms, bonding, and molecular polarity. So when we're talking about biology, the reason we have to look at bonds is there are really only 6 types of atoms that make up the majority of all living things. 99%, in fact, of all the atoms in living things are 6 atoms. So we're going to take a look at how those atoms interact and the ways that they interact to make the variety of living things that exist. So first of all, let's go back to our chemistry basics. What are the subatomic particles? Well, we have protons and neutrons in the nucleus, the protons being positively charged, neutrons being neutral, and the electrons are negatively charged, orbiting in electron orbitals around the nucleus. So when we look at a periodic table, we see the symbol, we see the atomic number, which can represent both the number of protons and the number of electrons in an atom, and then we also have the mass number, which is found by adding the number of protons and neutrons together, because electrons do not have significant mass, so they don't count in the mass of that element. So then we also have to look at isotopes. These are atoms of the same element, but they vary in the number of neutrons. Now that's important because as soon as you change protons, you've changed the element, but neutrons can change the mass, but it's still the same element. So for example, we can look at carbon 12, 13, and 14. Okay, 98.9% of all carbon in the world is carbon 12, meaning that it has 6 protons and 6 neutrons. But there are other isotopes or variations out there. Carbon 13 has 7 neutrons, carbon 14 has 8 neutrons. Now the numbers 13 and 14 are referring to their masses. So because they have the same number of electrons, all isotopes of an element usually have the same chemical properties or react the same. Everything that living things can do can be understood in the terms of the jigglings and wigglings of atoms. And that's essentially what we're going to do in this grade 12 university biology class is look at those electrons. Where do they go? Where do they come from? And what do they do? So let's dig a little bit deeper into those electrons. Why are they so important? Well, the chemical behavior of an atom is determined by the electrical configuration. Is it a full outer shell? Is it not a full outer shell? Are they shared equally? Are they not? So what we want to take a look at is that outermost or the valence shell of the atoms that we're looking at. So in this case, we have fluorine. It only has 7 valence electrons, meaning that it does not have a full shell. Atoms with an incomplete valence shell are very chemically reactive. So they will gain or lose electrons or share electrons to try to seek stability. When they have a full outer shell, they are considered happy. Intramolecular bonds. Intramolecular meaning within a molecule, intra, within. So bonds are formed by either the sharing or the transfer of electrons, meaning we have 2 major types of bonds. We have ionic bonds, which is the transfer of electrons, and we have covalent bonds, which is the sharing of electrons. So let's take a look at ions and the way that they seek stability or that full outer shell. Let's take a look at cations. Cations are a positively charged ion, meaning that they have lost an electron. So let's take a look at lithium. It only has 1 electron in its valence shell. It could either lose that 1 or gain 7 to try to fill that shell because 8 is what it needs. It's easier to lose the 1, therefore it gains a positive charge because it has more protons. Anions, conversely, are negatively charged because they have gained electrons, like this example of fluorine. So this is a reminder of the octet rule. Atoms tend to gain or lose or share electrons to have 8 electrons or a full outer shell. So ionic bonds occur when one atom donates or gives up 1 or more electrons. So sodium donates its electron to chlorine, making it a sodium ion, and a chloride ion, making sodium chloride. Positives and negatives attract to each other, almost like magnets. So those opposite charges attract, you now have an ionic compound. Covalent bonds, however, involve the sharing of a pair of valence electrons. So each atom involved in that bond will share 1 electron. So in a single bond, there are actually 2 electrons, 1 from each of those atoms. You can have a double bond, meaning there are 4 electrons total, 2 from each of the atoms. Right? We can have multiple configurations, but the idea is those electrons spend some time with one atom, some time with another. So we have multiple single, double, and there are even triple covalent bonds as well, but not shown here. When we look at a biological molecule like glucose, all of these lines are representing covalent bonds. So this leads us into polarity, or the sharing of those electrons, or the separation of electric charge, meaning that are those electrons shared equally or not? So when we have a molecule like water, or H2O, we look at and we can say oxygen is a much bigger element, much bigger atom. It's going to have a stronger pull. Therefore, it is going to be able to outpull those electrons, not completely rip them away from the hydrogens, but they're going to spend much more time with oxygen than they're going to spend with hydrogen. This is where the idea of polarity comes in, equal or unequal sharing. So I'm going to go through 2 examples, and then we'll summarize it in a chart in your note template. So polar covalent bonds are when electrons are shared unequally, such as the example of water we just mentioned, or chlorine or hydrogen. Notice little buddy here, clearly not sharing equally with his other buddy. Still sharing, but not equal. Non-polar covalent bonds is when electrons are shared equally, such as in an oxygen atom. But if we notice oxygen, well, of course they're going to be shared equally because 2 oxygens have the same pull. But you can have something like carbon dioxide when even though the pull between the carbon and oxygen is not equal, both oxygens are pulling with the same but opposite forces, which would cancel out. Therefore, they are shared equally. So let's summarize in terms of a chart. 2 types of covalent bonds. We have polar and non-polar. In our polar, we have unequal sharing of electrons. Non-polar, we have equal sharing. That electron spends equal time between and around both atoms. This is determined by electronegativity, whether those bonds are polar or non-polar. Electronegativity is the difference in electric pull of those different atoms. Now, if the difference is between 0.5 and 1.7, we consider it a polar covalent bond. If it is less than 0.5, now sometimes we can say or equal to, it is non-polar. Notice that 0.5 is kind of that gray area, whether it's polar or non-polar. Not only is it electronegativity, but also molecule symmetry that will lead to whether it is a polar or non-polar. So let's take a look at electronegativity. If we have 2 atoms here, we want to know which one has the ability to attract electrons more than the other. The more electronegativity they have, the larger their value, the stronger the pull they have. Well, chlorine has a value of 3, hydrogen of 2.1. So the difference is 0.9. So we refer back and we say, if it is between 0.5 and 1.7, it's a polar bond. Anything greater than 1.7, that pull would actually rip the electrons away from the other atom, making it ionic. Another couple examples, we have hydrogen and fluorine. The difference would be 1.9. It's an ionic bond. If you have 2 elements that are exactly the same, well, the difference is going to be 0. So that it's going to be non-polar or equal sharing. So oxygen, clearly non-polar molecule, equal sharing. Well, what if there are different elements involved? Carbon tetrachloride is also non-polar. This is where symmetry comes into play. So we look and we say the electronegativity between the carbon and the chloride is 0.5. That's that gray area. But we look at all of the pulls. Those pulls would all actually cancel each other out. It is a symmetrical molecule or symmetrical pulls, meaning that it is non-polar. So shape also dictates polarity. So if we look at some of these molecules here, this molecule is polar, even though it's symmetrical, but it's polar because there's an unequal pull in that bond. When we look at this bond, this molecule here, it is also polar. Why? Because we have an unbound pair of electrons, making this an asymmetrical molecule. This one down here is non-polar because it is completely symmetrical. If we were to draw a line down the middle, it would be completely symmetrical, meaning that all of those poles would cancel each other out. Be like a tug of war for the electrons, having everybody equal pull opposite directions. This one's also non-polar because it is symmetrical. Now we look at this last one and we say, well, it's the same shape as that, so it has to be non-polar. Not so quick. We have to take a look at the elements. They are not the same. So the fact that chloride has much stronger pull than the hydrogens, even though it is symmetrical, they have asymmetrical pulls on the electrons, making it a polar molecule. So polar molecules have what are called dipoles, which is a charge due to unequal sharing. The molecule as a whole, neutral. But we can have parts that act like they're charged because electrons spend more or less time there. So for example, in this one, the oxygen is slightly negative because electrons spend more time there. The hydrogens are slightly positive, usually denoted in this format here.